right, guys, let's go head down to the river and test the water chemistry.
We're here with River Source to do some community science, to see how healthy this river is for fish and for people. We're here at the Santa Fe River today, but we could be at any river in New Mexico doing this kind of work.
We're happy to be here with you guys to get an understanding of the health of the river. We're going to be looking at it from the water chemistry perspective. How healthy is the water by looking at simple things such as pH, total dissolved solids, the temperature of the water, dissolved oxygen, and the nutrients that we find in the water. Tommy, you're going to take temperature. Raylyn, you are going to measure pH. So as Tommy's measuring temperature, he's measuring temperature in degrees Celsius, which is the standard unit utilized around the world. Raylyn is going to be measuring pH. pH is a measure of how much acid or base is within the water. 73, it's probably a 7.3.
I got 7.3 pH. I got 12 degrees Celsius.
Hey, my name's Ari, and I did a science project for the science fair about total dissolved solids, and this is the total dissolved solids tester. It tests how much TDS is in the water. I got 90 parts per million.
The next test that we're going to run is turbidity. Turbidity is a measure of how much dirt or sediment is within the water. One of the things that my kids did after they collected the sample was to clean the vial to make sure that there wasn't any mud or fingerprints on here, as this meter, the turbidity meter, uses light to shoot through the vial and the sample to determine how much sediment is within that water. And so I'll be running my test. We line up this arrow with that arrow on the meter, and we press the read button. And it takes a few moments because it's actually taking multiple readings of the turbidity. Okay, and so the reading on the turbidity meter is 8.20, which is a really low reading for turbidity. The units for turbidity is NTU, which is called a nephelometric turbidity unit. Most important things to also consider is that we have a very good quality sample cell, that it is clean. We normally will clean our vials before and after every trip. Another thing is to make sure that there are no scratches or any oddities on the outside of the vial. And then I oftentimes will use my shirt in order to clean the vial to make sure that there's no fingerprints or mud.
So now we're going to measure the nutrients in the stream, and that can really impact how much algae starts to bloom in the stream, and then also how much oxygen's in the water. If you get a lot of algae because of excessive nutrients, then you can have a big crash in oxygen when that algae starts to die. To measure nutrients, we use a Hawk colorimeter. This one is provided by the New Mexico Department of Game and Fish. And we use 2 sample cells. We use one sample cell as what we call the blank, or essentially the 0 value, which is going to tell the colorimeter what the river water looks like without any added reagents. Okay, now we're going to run the colorimeter test, which can tell us the concentration of nitrate nitrogen or reactive phosphorus. We're going to use an instruction guide from the Hawk Company on how to use this machine. So we've made a photocopy of it and put it inside a sheet protector, and this 2-sided sheet right here is going to tell us what to do. The first thing that we need to do is go ahead and program the machine so that it's going to be reading for the right test. This says press the program button and 7-9, and then I press enter, and then it's going to dial in to the right test that we want to take. And we have 2 types of powder pillows. One, the smaller one is for nitrates, one is for phosphorus. We're going to go ahead and start the phosphorus colorimeter test right now. So what I'm going to do is I'm going to identify which of these sample cells is going to be my blank. I'm not going to add anything to it. I'm going to set that to the side over here, and then I'm going to go ahead and open the cap for this one and add all the contents from this reactive phosphorus powder pillow. And if there is phosphorus in the water, the color signature for this particular element is blue. And then I'm going to give it a tap. And then I'm going to cap it, and then I'm going to use a timer to measure 15 seconds, and I'm going to shake it for 15 seconds. Okay, now my timer says I've shaken it for 15 seconds, and now I need to press the timer on this machine, and it's going to count down from 2 minutes. And then when it's done, it's going to beep. Okay, we're almost ready. We've got 26 seconds to wait. Let's just see right now with our eyes if there's a little bit of a difference in color. I am not seeing much of a color difference. Do you? But the machine can read things that are very subtle. Let's put it against a white background. Maybe it looks a little bit bluer right there. All right, 2 seconds, 1 second, and it's beeping. All right, so the first thing I'm going to do before we run the test, now that the 2 minutes is done, the first thing that I'm going to do is just double check to make sure the sample cells are nice and clean. This is my blank. I'm going to test that first. And then this is my prepared sample that had the reagent put in it. And the machine needs to read the blank first. And so there's a diamond right on the front of that. I'm going to line that up towards the screen, and then I'm going to put this light shield over the top. And then I'm going to press the 0 button. It should say 0. Okay, it does. So that's good. The machine now knows what river water looks like without any reagent. How blue is it? Now I'm going to put in the prepared sample, and I'm going to ask it to read again, and it's going to measure the difference in how intense that color blue is. So I'm going to press read. Next, and I've got a result of 0.16 milligrams per liter, or parts per million. They're the same. What's really good about this value is that in New Mexico, 0.16 is not a problem. A lot of our waters have a similar concentration as this. But if you were taking a measurement and you got the same value, say in the state of Connecticut or Massachusetts, this probably would be a violation of a water quality standard. In New Mexico, we have a lot of phosphorus in our soils, and so our water tends to have more phosphorus in it. In many rivers in New Mexico, there are no standards for phosphorus, but we still use it because if it gets to 1 milligram or 2 milligrams per liter phosphorus, we know there's likely some source of excess nutrients of phosphorus coming into the stream. Okay, now we're going to run the nitrate test. I'm going to put in the blank first. I've cleaned off the sample cell. I'm going to put on the light shield. I'm going to press 0. I'm going to zero it out with the blank. And it read 0 there. Now I'm going to go ahead and put in the prepared sample and measure that. And I'm going to press read, and it's going to read the difference. 0.4 milligrams per liter of nitrates, and that's well below the 10 milligram per liter threshold for humans, and it's pretty low for what we'd find in a natural stream. So that's a good result.
Okay, Tommy, the next test that we're going to do is dissolved oxygen. One of the most important things about this test is to make sure that we fill this up without any air bubbles. Do you know how we do that?
Yeah, we just dip it underwater.
You fill it up all the way underwater and cap it when it's under the water, but make sure to rinse it twice before you fill it up, okay? Testing for dissolved oxygen is one of the hardest tests to perform to make sure that you collect the sample without any air bubbles in there. Okay, so I'm gonna get set up with my dissolved oxygen kit. One thing that we like to teach our students that there's a lot of great information within this dissolved oxygen manual. When we're in a hurry to collect samples in the field, we can utilize the short form instructions on the back that outlines which different chemicals we are going to utilize in what different order. It's a lot like baking. What different chemicals are we going to add first, second, third, and how much are we going to utilize of them? So if I read these instructions, it says to fill the sampling water bottle and then add 8 drops of manganese sulfate solution. So we got our manganese sulfate solution there, and we're going to add 8 drops. The next part of the test says to add 8 drops of alkali potassium iodide azide. You notice when I'm adding these drops, I'm holding the dropper a little bit above the bottle so that I can keep track or even count how many drops I put in there. I didn't do it last time, but this time I'll count them for you so that you can see that I'm keeping track. 1, 2, 3, 4, 5, 6, 7, 8, and we are good to go. So after I've added the manganese sulfate and the alkali potassium iodide azide, I shake up my sample really well. What you're going to notice is that the sample turns something that looks a lot like apple juice, or apple juice with floaties, I like to call it. I like to see these different color changes when I'm running this test, because then it tells me that I'm running the test properly. If you do not see these color changes that I'm going to go through with you guys, then that means that maybe you made an error. Remember, it is okay that if you're not sure you did something properly, to run the test again. The brown material that we formed within our dissolved oxygen sample is what's known as a precipitate. It's a solid structure that has formed, a solid chemical structure that has formed within the water. What we'll find is that precipitate is heavier than the water, and so we need to allow some time for that precipitate to settle. So we'll set this down here and give it a few moments in order to settle. So while we're waiting for the dissolved oxygen sample to settle, we can talk about where the dissolved oxygen comes from in the water and why is it important for the fish that live within this water. Okay, as you notice in a riffle that's located behind me here, a riffle is an area that is formed because the water is flowing over a lot of cobbles or similar rocks that you see here along the shore. As that water flows over these rocks, it creates turbulence as that water moves over the rocks. It causes that water, as you see in here, to form even bubbles as it moves over those rocks. And as the water moves through these riffle types of habitats, it causes an increase in dissolved oxygen as it's causing that water to mix up. Okay, the other interesting fact about riffles when we're monitoring in the river is that these are great homes for foods such as benthic macroinvertebrates that we've talked about before. The benthic macroinvertebrates provide food for the fish species that could be living in here. And as you see, the swallows are flying over the river right now. There's a good chance that they could be eating or harvesting the benthic macroinvertebrates that are emerging or hatching, as we might call it, during the day today. When temperatures get warmer, then the benthic macroinvertebrates emerge. Okay, so it looks like our sample has settled. The way that I can tell this is if I'm going to hold up my sample for you, and as you notice, the brown precipitate is sitting on the bottom of the vial. It's now time to move on to the next step. So according to this, I will now place in 8 drops of sulfuric acid. This is probably the most hazardous chemical that we have here, but it's not very strong acid. It's not going to burn your skin or hurt you. The main issue is that it shouldn't be ingested. Since we're only using 8 drops of it, it limits the hazard that we have. Again, you want to make sure that we're being careful when we utilize this. Okay, so almost immediately you'll see that the precipitate begins to dissolve and you start getting more of like a clear apple juice color. And so what I'm going to do is I'm going to continue to shake this until the precipitate dissolves, or all those little brown specks that you see in there disappear. When we're shaking chemicals, we normally want to shake side to side. We do not want to shake back and forth because that has the ability to splash chemicals into your eyes. Okay, so I've continued to shake long enough so that I can see that all of those precipitates have dissolved and we now have a clear apple juice looking solution. So the next part of the test tells me to get the 20 milliliter test tube and fill it up to the 20 milliliter line. And then so I'm going to slowly pour this until we reach that 20 milliliter line. It looks like I poured a little bit too much, so I'm going to pour a tiny bit back. And remember, when you're measuring stuff using glassware, we want to think about a term called the meniscus, the curvature of the water or the solution that we see in the sampling vial. So we want to make sure that that meniscus, as it contacts the vial, that meets right up to the 20 milliliter line. Okay, the next part of the test says to fill the titrator. The titrator is something that looks like a syringe. The syringe is a way to measure how much of a solution we are going to need in order to titrate that sample. As you heard me say the term titrate, as you heard me say the term titration, is almost like a chemistry experiment where we're trying to figure out how much of one solution it takes to balance out another solution. Since the last liquid that we placed in there was an acid, the sulfuric acid, we are going to be utilizing a base in order to balance out that acid. So according to the instructions here, it says to fill the titrator with sodium thiosulfate, and that is the base that we're going to use in the titration. There is a trick to filling the syringe as well, and we want to fill it without any air bubbles. The easiest way to do that is to fill it up upside down. Okay, so what I'm going to do is fill it up partially. And what I've noticed is as I start filling it, there's an air bubble present within that sample. So I'm going to push all the air up. I may actually do it twice because it looks like there's still an air bubble in there. That pushes the air bubble into the top of the bottle there. And then we fill up our titrator to the 0 mark. And so now it says to titrate until the sample color is pale yellow. When we're titrating, what we want to do is add a small amount or several or just a few drops at a time. When we're titrating, we want to add 1 drop at a time and then shake it. We do not need to remove the titrator. Every time we shake it, we'll just add a drop and shake it. Okay, it looks like my color may be a little bit pale looking or lighter than it was before. One great way in order to determine if it's more of a pale yellow color is to put your samples next to each other and see what they look like. It does appear to be more pale yellow. Okay, so once it's pale yellow, it says to add 8 drops of starch indicator. Starch is one of the most commonly used indicators for acid solutions. When you place starch in an acid solution, it turns a particular color which is easy to see. And so again, this one I'm going to add 8 drops. 1, 2, 3, 4, 5, 6, 7, 8. And so as you can see, it's formed almost a purple or a black color. Once we've got this black or purple color, we then continue to titrate until the blue or black color just disappears. So again, I'm going to add my sodium thiosulfate 1 drop at a time. If you do this really slowly, you'll actually start to see something that looks like clouds as you add your sodium thiosulfate. And I always like to hold these samples well up in the air so that I can see the color change. And with that 1 drop, our sample now appears clear. So that's how we know that we are done with our titration. Okay, so we can now get our value for dissolved oxygen by reading this titrator here. Okay, it looks like our reading is a 6.8, but again, we need to consider the units. The unit of measurement for dissolved oxygen is milligrams per liter. If we have a liter of water, how many milligrams of dissolved oxygen are present within that liter? So one other thing to consider as we're running samples that require using chemicals that could be toxic or hazardous to the environment is to take special care that we're utilizing them properly and that we're not spilling them on the ground. And even after we run these samples, any waste that we create is going to go into a waste bottle. The waste bottle, it just helps us to keep any hazardous materials or chemicals that we're utilizing out of the environment.